All right, looks like we're all set up now. My name is Brett Hoyer. I am a senior software engineer here at Yugabyte on the developer relations team. Many of you who are just coming over from Frank's workshop on database indexing might find that Frank has frankly forgotten more about databases than I will ever know. I'm more of an applications developer, working here at Yugabyte to test emerging technologies on the database and evangelize the database. Previously, I've worked at big data startups, IoT startups, and I was working at Oracle on the IoT team, so working with a lot of big data and data at scale. So today I'm going to be giving a talk on GenAI applications, how to build them, how they fit into the Postgres ecosystem, and frankly, whether or not you need a dedicated vector database in that ecosystem. I know nowadays, GenAI, AI, everything having to do with building AI agents is at the forefront of emerging tech, probably to the point of exhaustion for a lot of us. So I'm hoping to demystify a lot of what is going on in this ecosystem and provide you with a little bit of context for how you can get started building these applications pretty simply. We're not going to be building anything wildly complicated, but with the building blocks that I'm going to show through a series of Jupyter notebooks in Python, we'll be able to see how we can fit these pieces together to start building more complex AI agents that can back applications or just help you with general tasks that you might have in your organization. So before we get started, there are several things that need to be set up. Working with AI is a little bit more cumbersome than just the standard setup, installing package dependencies for web development or otherwise. So what I would ask people to do, if you would like to follow along live and actually code yourself, you can go ahead and check out my GitHub and clone this repository. And this is what we'll be working throughout this presentation. Also, totally fine if you don't care to do that or you'd like to do it later on. I'd be happy to answer any questions that you might have offline if you'd like to ping me on LinkedIn or in our community Slack channel here at Yugabyte. But for anyone who wants to follow along and work with the Jupyter notebooks, I would recommend cloning this repository. So before we get into the code, and I promise that I will not be hanging on slides for too long here, but I want to demystify some of the buzzwords in emerging tech. As I mentioned, I've worked previously in big data and IoT. It seems like I'm just moving from one emerging tech to another. I'm just maybe I'll need to get into NFTs next. That'll be my I'll collected all of the emerging tech at that point. So what I wanted to get through is the fact that there are so many buzzwords that it's almost disgusting, and many of these I'm hoping to demystify or clarify for you today. Namely, we'll be working with large language models. We'll touch on multimodal models using Postgres as a vector database. We will be executing semantic search by creating vector representations of text and storing them in the database using pgvector. We might touch on hallucinations being when an LLM produces a response that is wild or off base or confusing. Then there are various things that are here are underpinnings of the AI applications here. Vector embeddings, pre-training being the process when a large language model is trained on a vast data set. Fine-tuning being when that model is taken and fine-tuned through either artificial means or by human intervention to sort of make that model more tailored towards a particular use case. Retrieval augmented generation is when you are pulling from data sources that are inherent to your application, your business, splitting up that data into chunks and storing it in a vector representation such that it can be accessed in your AI applications. And contextual memory being the memory that is available to an LLM, a chatbot, in a conversation that you are having. And this is just about 1/100th. Excuse me, I'm not sure how that is just about 1/100th of the terms. It is absolutely exhausting. People will use different terms to mean different things. So we will be working through this throughout this presentation to further clarify, and of course, ask as many questions as you would like. I might not be an expert in a particular domain here in AI in particular, but I will be happy to do a little research and get back to you if I do not have the answer immediately. So let's define what AI agents are, or rather, I will provide the definition that I stole directly from ChatGPT, which is that AI agents are autonomous or semi-autonomous systems that can perceive, reason, and take actions within an environment to achieve specific goals. So you might have heard the term react agents. That is a common type of AI agent. And the name, it came by it honestly. These agents are able to react based on the data that they are given to make decisions and to invoke particular actions. There are several models here. I would like to dive into OpenAI in particular. We will be working with a couple OpenAI models here. So as we know, there are GPT-4o is the latest model. There are also smaller context windows or smaller models that might produce less embeddings in our embedding models here through ChatGPT. But there are also other types of models. Namely, there are multimodal models that are available to ingest more than just text. So we might be able to infer based on an image what the description of that image might be, to create captions in your applications, or rather just to execute search based on an image directly. So there are all sorts of models available here, and I recommend looking through this list. If we go down to embeddings, we can see that OpenAI has a few models listed here for embeddings. So what are embedding models? We will be getting into that shortly, but what I would like to mention is that based on the embedding model that you have selected, you will have a different number of dimensions output from the model. We'll be getting into that further, but this will impact how you set up your database schema based on the number of dimensions of the embedding model that you are choosing to use. So here's what I wanted to show. So we think of OpenAI as being, an LLM. We're interacting with a large language model. We are prompting it with a question, and it is providing a series of characters, words, sentences, paragraphs to generate a response based on what it was prompted. That is what it has been trained to do. But if we come into ChatGPT and ask ChatGPT, what is ChatGPT? Can it be considered an AI agent? So here we can see that ChatGPT, while thought of as an LLM, OpenAI is creating models. They're spending tens, potentially hundreds of millions of dollars training these models on such a vast data set, basically for simplicity's sake, a download of the internet, we can think. And they're producing these models that we're running. So here I'm running the latest model, GPT-4o, but there are other models available as well. But OpenAI, ChatGPT in particular, can be thought of as an AI agent. It's able to make decisions based on what is being presented to it. And it has access to more than just the model itself in doing so. So in AI agents, there is the concept of tools. You provide tools to the agent, which are essentially just functions. We can reduce them down to think of them as functions that the agent is aware of, and they can take certain actions. So we can ask, what tools does ChatGPT have access to? And this might not be a comprehensive list, but we can see that ChatGPT has access to Python. It can execute Python code. It has access to a web browser, so it's able to get up-to-date information based on what is happening, that is more recent than when the model was last trained. As I mentioned, it costs tens or hundreds of millions of dollars to train models at these premier companies, Anthropic, OpenAI, Google, and so forth. So adding these tools that can access the internet makes the responses much more reasoned about, and just allows us to have better responses. So that is something that I wanted to mention because it does become a bit confusing. Like, is everything just an AI agent? What is an LLM? What is an AI agent? How do these things work together? I hope that clears that up for some people. So I mentioned previously, briefly, that OpenAI also has embedding models, as do all of the other providers that I just mentioned. So what are vector embeddings, and do you need a dedicated vector database? So embedding models essentially take a medium, a data source. Most often it will take text, but embedding models are developed to also take image, speech, video, and these bits of data can be broken down into a multi-dimensional vector array, an array of embeddings. And each of these embeddings can be compared against one another in order to find similarity between the various data points in a data set. So we can think of of a very simple example, we might send the cat in the hat to the OpenAI embedding model, and it might provide a 1,536 dimensional array, which are just a large array of floats, essentially. So there are some vector databases, and I'm sure many people looking to build AI applications will find code samples that are leaning heavily on Pinecone or Chroma in the examples, and for good reason. They are made efficient for storing, querying, indexing embeddings. But this is no longer necessary. Like we found with many other things in the SQL ecosystem, with Postgres becoming the most popular database of choice for many developers. Vectors are now available to be stored directly within your general purpose source of truth database, that being Postgres. So using pgvector, we are able to store vector embeddings and eliminate the need to manage multiple database connections. I think everyone understands why that might be nice. So very quickly, this is what it looks like to interact with pgvector in Postgres. We simply install pgvector as an extension, the vector extension, and this gives us access to a vector data type. As we can see here, we are specifying 1,536 dimensions. So this number here, when we are setting up our DDL, is dependent on the embedding model that we are using. I will say that multiple times. So if you should choose to change your embedding model and generate new embeddings for your data set, you will need to make sure that you are updating this column appropriately. And then we can insert, just like we would any other data to our database. And we are just going to be supplying this vector array in our insert to the database. And there are numerous operators available to us in pgvector for finding similarity or difference between elements in our data set. When we are doing similarity search, namely semantic search in text, which is the most popular use case, I would say that the large majority of people are using cosine similarity. That is what this symbol is indicating here. So we are, in this query, we are selecting all of our Airbnb listings, and we are using the embedding of the description column. We're using this array that was generated based on the description of the listings. And based on our query, we're able to rank, essentially. We're able to sort by that similarity. So I have a link here to open. And this shows pgvector has multiple different operators, and we can see there are numerous operators: Euclidean distance, negative inner product, cosine distance. Some of these were added later on. I would say that cosine distance and Euclidean distance are the most popular, but depending on your use case, you will need to read through this documentation to find what you're looking for. Also, there are indexes that are specific to vectors, namely the HNSW and the IVF flat indexes. HNSW is better for data that is changing frequently. The index does not need to be, recompiled every time new data is being added to the data set, where IVF flat is better for, just a one-shot index for seldom changing data. And we can show this while we won't be going into indexing in this presentation. Obviously, Frank just spoke the praises of indexing for 2 hours, and everyone knows that they will significantly speed up query performance. I have a guide to pgvector that goes into a lot of these concepts. You can find it on our blog, and it will discuss all of these things in more detail, including the derivation of some of these formulas that are the underpinning of the operators that are being used, how you can derive cosine similarity from cosine distance. Can get as nerdy as you would like looking into this. So I encourage you to do so. So let me see, do we have any questions? No questions yet. I can now go into my project. I am running Jupyter notebooks inside of Visual Studio Code. However, if you'd like, you can run them in your browser just by running Jupyter notebooks in the command line. But what I have here, if we go to the main README for the project, we can see that I've just set up links to all of the various sections here in the project, and we can start with installing the prerequisites. So to get started with this environment, and we will be going through some of these prerequisites. Some are, nice to have. Some are hard stop requirements for following along with these demos. But really what I'm trying to achieve is not to have a super demo-y demo. I want people to learn these concepts, to be able to play around a little bit and to actually have an ecosystem for building your own applications after this 2-hour or less workshop. So Python is the language of choice for data science and AI applications, although the LangChain framework, LangChain and LangGraph ecosystem is also available in JavaScript. But most examples that you find will still be in Python. We'll need pip for installing packages and creating a virtual environment. Git, self-explanatory. Docker desktop is where I am running Postgres and Yugabyte. If you choose to run this application using Yugabyte, you are more than welcome to. There's relative parity between running on Postgres and Yugabyte, other than the ports and connection details. And we have a team here currently working strictly on adding indexing and various other features for vector databases in YugabyteDB. So you can check in for a beta of that coming very, very soon, if not just released. Then I developed some of these modules with the ability to run on OpenAI or Ollama. So let me show what Ollama is. So Ollama can be downloaded from ollama.com, and it gives you the ability to run models locally on your own machine, which is great because you don't need to pay for the use of them. And there's a command line utility for interacting with this tool. So for instance, you can run Meta's open sourced model directly here on your machine if you have the hardware necessary to do so, and it won't bog your system down. And there are also embedding models available. So if you want to build any applications without using up a bunch of tokens and having to register API keys and spending a bunch of money at OpenAI or wherever, although I will tell you that it does not cost a lot of money to run any of these samples. It should just be, pennies on the dollar. And I will be using OpenAI throughout this workshop because I find that the responses from OpenAI are significantly better than some of these open source tools. But nonetheless, it is nice to know that you are able to run locally should you choose to do so here. PSQL, command line utility, just nice to be able to interact with the database from outside of the database containers. And if you want to use OpenAI or the Tavily search tool, I would ask that you create accounts and create API keys for each of these. So we have a workshop requirements.txt file with all of the various dependencies for this workshop. And I'm going to go ahead. Do you want to select it for the work? Sure. So I'm creating an environment here. We can see here that I've created workshop env. And here, let me go back to my. Here we can activate this environment. So hopefully everyone can see this clearly. I've activated the environment and we can see that we are now inside of this environment. After doing so, we can install all of these dependencies that are listed inside of the workshop requirements.txt file. And then we have our own little sandboxed environment to work with all of the dependencies, or hopefully all of the dependencies included there, such that we're not polluting the global, package namespace for our Python distribution on our machine. So let's see, did this do its thing? Okay, too many active changes. All right, so we are inside of our workspace, our environment, and we have installed all of our dependencies. Now I can go to the .env example file, and we can see that Postgres connection details are provided here. A Tavily API key needs to be supplied, and you can choose which ecosystem you would like to be working with between OpenAI or Ollama in this case. Although, as I said, you should consider using OpenAI, otherwise you will need to make changes here and there to certain modules in order to run them. Somewhere where something might say chat OpenAI, you might need to use the chat Ollama package, for instance. So that is something to note. And you will create an .env file in the root of this project from this env example. All right, so we have the prerequisites out of the way. Let's go to database setup. So database setup, we have our env file we already mentioned, And I have a Docker compose file here to just immediately spin up a Postgres instance with pgvector enabled on it. And this image is made available by the pgvector team. This is an open source project, but they are pushing Docker images, and this will be connected on the environment variables that you should set in your env file. And we can connect to this database. I have it running currently. And we can see here, I guess I have, oh, maybe not. So we can see that we have bookings, customers, listings, Olama, listings, OpenAI. So what I've done is I've gone ahead and generated embeddings for Olama and OpenAI already and added these to the database. So I've added utility functions for generating embeddings and doing this by hitting the OpenAI API. But I've already generated these embeddings and put them in GitHub in the repository via these files, listings with embeddings, and it shows the model that was used to generate these embeddings. So we can use these CSV files to populate the database, and that makes life a lot easier for you as the end user of this workshop, because you won't need to spend the time waiting for that to complete. So working with our vector data set, we can set PG passwords so that we don't need to supply a password every time we are working with the command line utility. And as I mentioned, set the embedding model that you should choose to use. I've created a generate embeddings utility function that can call each of these ecosystems. So if we go into generate embeddings, hopefully people can see. I'm going to make this a little bit smaller. When we call get embeddings, based on the ecosystem that we are in, we have different ways of generating embeddings, either locally for Olama or by pinging the client that is made available through a Python package. And I have a process CSV embeddings function that can iterate over our data set that we have in the repository in the listings.csv file. It'll iterate over the description column of each Airbnb listing. There's some like 7,000 to 8,000 listings in here in the San Francisco Bay Area. This is a publicly available data set that I downloaded. And it will output the output CSV file at the in the root at the file that you supply here. So we are able to generate that data set using that function, and that is what I used to generate the files previously. Then we're able to run just a simple command to copy. After importing our schema for OpenAI would be preferable. We can copy the CSV that is output from the generate embeddings file, and we can copy that directly into our database for use. So I can show, if I go to my terminal, So if we select count star from listings OpenAI, we can see that we have 7,807 listings in the database with the corresponding embeddings for them. So that is all squared away. Of course, you can follow these instructions on your own machine, either now or anytime in the future. And if you run into any issues, please do let me know. So now that we have some of the prerequisites out of the way, hopefully all of that was relatively clear. I know that it's not super cut and dry setting up some of these prerequisites, but now I actually want to get into running code on the database. So I'm going to do that via Jupyter Notebook. So Jupyter Notebook allows us to execute Python code. You can run this in the root directory here just by running Jupyter with a Y notebook from the command line from your terminal in our virtual environment here. This should be installed. And we can run this. Sorry, my computer is choosing to update at the worst time ever. So we can run the various code blocks in notebooks in order to, iteratively build a program. So instead of having a file with all of the code written in it and executed all at once, we can just run through block by block for demonstration purposes. So here we're loading our environment from our env file using the python.env package. And we can use these variables that we're setting from the environment to connect to our database. So here we can see that we are using a local Postgres database. I'm doing that within Docker Compose. We can see here that I'm running both Yugabyte and Postgres, actually. Postgres on 5432 and Yugabyte on 5433, which are the default ports. And here we can test the connection to the database. And we can see that we're connecting successfully to the database from Python using the package for Python. And now we can run the utility functions that I mentioned previously. Not only did I create a function to get embeddings from OpenAI and Ollama, but I also created a function to test cosine similarity between vectors in the database. So we can run this code, and what we will do is we will get an embedding of the text that I provide, and we will test the cosine similarity against the database. So here I'll say, find a place by Golden Gate Park and the beach. I live here in San Francisco, and this data set happens to be from San Francisco as well. So here we can see we are printing our embedding. So we have this very long array as promised, 1,536 vectors to be exact. And we are returning a series of listings from the database. So here, if we go to test embeddings, test cosine similarity. So test cosine similarity allows us to execute a query against the database, and it's returning, the name of the neighborhood, the description, and we are doing a cosine similarity search against the database to order our responses. So we are seeing that this is being printed out in the format that I asked for. And the cosine similarity values are being provided. So cosine similarity, one meaning that the record is most similar to the embedding vectors, and 0 meaning that there is absolutely no similarity between them. So based on what I asked for a place by Golden Gate Park, I believe, and the beach. And we can see here that in the very first response, the description that has been embedded mentions both Golden Gate Park and the beach. So it is doing a very good job at returning exactly what I asked for. Here I chose to print out that we are using GPT-4o mini as our LLM model. And then I think we can do embedding model as well. So our embedding model is text embedding 3 small, which is 1,536 dimensions, I believe. Yeah, we can run this as well. And we are getting embeddings for a place by Golden Gate Bridge and Fort Mason, slightly different. And here we can see that we have a different result coming back. And for those of you who live in San Francisco, you'll know that this is actually a very good response. Fort Mason is closer to the Marina District, and these neighborhoods that were returned previously near Golden Gate Park are the Sunset and the Richmond. So this is all working great. So we can move on now. We've seen how pgvector works in at least limited detail here. So I want to get through to some more pointed examples here. We've already covered the underpinnings of your AI applications. It genuinely is as simple as what I just described at its core. We are just storing embeddings in the database. We'll see now in this RAG example that sometimes we need to split the text into multiple sections in order to embed it. We might want to have overlap between the various sections that are being embedded for different reasons. There are caveats to everything that I'm speaking about, and I'm not trying to gloss over various complexities, but it is truly as simple as what I just showed in terms of getting started, embedding text, and using that in queries in Postgres. So here I'm going to show an example of retrieval augmented generation, which is essentially using data sources available to you in order to create embeddings sort of on the fly. That's not the best definition. Retrieval augmented generation, a good example would be, scraping a Wikipedia page and creating embeddings from that page, or supplying a program with a set of financial documents or legal PDFs and splitting them up into chunks so that they can be searched more efficiently in your database. These are examples of RAG systems. So what I'm going to do here is use the pgvector package that is available in the LangChain ecosystem. So LangChain is probably the most popular framework for, and it's fully open sourced, for building AI applications. You'll find that LangChain, the API can be a little bit confusing, as is always the case with emerging tech. Things are being changed constantly, and you might find that certain things become outdated quickly, and we will get into that more as we go. But I'm going to show how we can read a file, a PDF that I've added to our repository. We have a PDF here that is actually just a download of the Wikipedia page for SQL. Not the most exciting thing in the world, but I wanted to show that we can create a simple RAG system directly here on our machine by splitting this PDF into multiple characters, into multiple chunks, and then embedding each of these chunks and storing them in the database using pgvector. So we have created our connection details. I could have read that from the end file. And here we're going to create a RAG example collection in the database. The PDF path, it's just available here at sql.pdf. And we're going to use this pgvector package that's available to us in LangChain. If you want to connect to use pgvector's operations directly within LangChain without creating an API endpoint or some intermediary code, you can directly do it with LangChain within a chain. So we can run this. I will drop my vector database. So here I have a vector database already created, and I'm going to drop it, and I'm going to recreate this database. Hopefully this works. Otherwise, that would be fairly embarrassing. Okay, so this database was created. What we did here, we looked for the presence of the vector DB, and it didn't exist, so we created it. And we also created the pgvector extension if it did not exist. And here what we can do, we can use the Python PDF loader to load the PDF into documents. We can then split the document into chunks. So the chunk size of 1,000 with 100 overlap, meaning that there will be some overlap between the different chunks. So we are splitting this up into different sections to embed using OpenAI. Not the most complicated thing in the world here. We are going to run this, and now, what did we call it? Vector DB is what we called it. So here we can see that this automatically created LangChain PG collection and LangChain PG embedding. So we have two tables here. If we count, select from LangChain PG embedding, we can see that we have 40 records in the database, 40 embeddings in the database. And here we can ask a question of the chain that we just created. LangChain creates chains, very sequential operations that are happening in the LangChain framework. We will later get into LangGraph, which is their graph-based approach to developing AI agents. So here we have created our vector store from the documents that were generated, all of the splits and the embeddings generated. We've created a collection based on the collection name. And here we're able to create a chain using this vector store as our retriever for question and answer. Don't get bogged down too much in the API details here. Obviously, you can consult the documentation of LangChain, but it's fairly self-explanatory how to link these things together once you get into it. Now we can run the ask question function, which we will do now. The question that I want answered from this PDF that we've embedded is, what are the basic SQL basic SQL select statement components. And I don't just want to know the components, but I also want to know, what metadata, what page was this derived from in the embeddings. Because that's often a huge problem in building these systems where we might arrive at a response, but we don't know anything about, the source behind the data. How can we trust that the LLM, the agent, is providing us with a reasonable response if we can't have a definitive source of the response? So here we're seeing the response to our question about the underpinnings of a select statement. We are finding that the answer is highly representative of the question, and there is a chart that is being documented as the source for the output. So there's a chart showing several elements comprising a single statement or query. So let's go to the Wikipedia page for SQL. And this is the chart that is being referenced, which clearly shows the different components of a query, or I believe that was it. Maybe there's another one for select, I'm not sure. But we can see that they did use something representative of finding the derivation of a query. So very nice. That is building a RAG system. And you can think about these things as building blocks, as I mentioned in the beginning. You can create an AI agent that communicates with a RAG system as well. So an AI agent might make a request out to a tool or some other link to a RAG system in order to inform its own decisions. And we can show how to do that in more detail using LangGraph, which honestly makes LangChain look juvenile, sort of a thing of the past, but again, under the same ecosystem. So we have gone over RAG-based systems, but let's talk about agents more specifically. Systems that are able to communicate with outside tools and make reasonable decisions based on all of the data available at its disposal, not just the data that it was trained on, but also additional data that it might have access to. So in order to run this module, you will need to have an API key set up for Tavily, Tavily being a tool for connecting LLMs to the web. So this is an industry leader for creating tailored results for LLMs and RAG-based systems. And there is a package for using this inside of Python. And we can see here that we can create a tool for the Tavily search results. So Tavily search results is a tool available in the LangChain community. As I mentioned previously, a tool is essentially just a block of code that can be executed and made known to an AI agent for execution. So you could tell an AI agent in the prompt that they have access to different tools, and based on a user's input, whether or not they should consider using a particular tool. So here with the Tavily search tool, I've created an API key for this tool. And I've chosen to respond with a maximum of 5 results from this web-based search tool. And we are able to execute or invoke the tool directly. This component doesn't need to be run just within the context of our agent. So I'm able to invoke what is the color of the sky? What color is the sky? And here we can see that the default response from this tool is an array of objects with URLs and a deduced version of what the answer might be to the question based on these sources. So you can see how we can get information from these tools and then use the output from those tools in order to feed data to our LLM to make more informed decisions. Or, we can combine data from multiple sources. We could use our RAG as well as Tavily, for instance, in order to give the LLM a better chance of providing accurate results. So here we can use the tool that we just created to create a tool calling agent inside of LangChain. So a tool calling agent is essentially a React agent that is made known of the Tavily search tool. So we can create a tool. We could either run the Tavily, provide the Tavily search results tool directly, or we can create our own tool, which is essentially just a function that can run any code. So we could have created a function here to connect to a database. Based on the user's input, we could execute queries. We could do any arbitrary number of things here. But here we just want to invoke the Tavily function and return the results back to the LLM. We can create a tools array. And we can add these tools to our tool calling agent so that when we're executing or invoking the agent, we have an LLM, we have tools, and we have a custom prompt. So our custom prompt is comprised of a system message, which is the message that is made available to the agent, telling the agent how it should behave. And then the human input here. So the human input being, what is being invoked? What is the question or the information that I would like to be getting out of this agent? Then we have this special thing here, which is the agent scratchpad. So this is one of the things that I find a little bit frustrating at times with LangChain. When you're using this, you're like, God, what is this placeholder agent scratchpad thing? And it's not super intuitive all the time. What this agent scratchpad is it's basically a memory bank for the agent to be able to reason about using different tools, storing its thought process along the way so that it knows, what paths it's gone down in trying to find the best response to whatever question you might have. So let me just make sure that I've run all of these so that we can continue operating here. We have instantiated our tool, and here we have created a tool calling agent and invoked that agent. So we have access to a tool in our tool calling agent. And what do I want to know? So I would like to know what is the weather in Mumbai today. So here we can see I've run the agent executor in verbose mode, which is going to print out all of the steps in executing this agent. So here we can see that the search tool has been called, which is exactly what we would expect. And it is yielding real-time results for weather. Of course, an LLM would not be able on its own to find real-time results because it was trained on data that obviously occurred at the time that training occurred. So here we're able to see that the weather in Mumbai is 81 degrees Fahrenheit today. It's overcast, blah, 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 blah. So this is an example of an agent execution. This, of course, could be run behind an API endpoint or in any other system that you should develop. But this is the underpinning for what I would like to continue showing, which is LangGraph. What we're seeing here with LangChain is a very sequential set of steps. We're creating our tools, creating our agent, executing our agent, but everything is being done very sequentially. Any looping back that you wish to do, any continued execution needs to sort of be architected on your own as an application developer. It's not super user-friendly for creating complex workflows that might be better suited for a graph, which is why the LangChain team created LangGraph. So LangGraph allows you to create agents with more agency, as listed here. But namely, you're able to make graph-based agents which allow you to interact with an assistant. You can interact with tools. You can interact with humans. Say there's something that you want the agent to be able to do, but you might get to a certain part in this graph that you don't want to execute without explicitly allowing it to do so. For instance, you might want an agent to help work as a travel or stockbroker, but you don't actually want to execute a booking of a listing and charge your credit card or execute a stock trade without a human saying, yes, definitely do that on my behalf. There are various other things that can be done with this very powerful program. And there are various tools made available in this ecosystem as well. So we will get into this now. Don't know if we have any questions. I'm not seeing anything at the moment. Oh, I'm seeing a question about getting the files for the workshop. You can get the files for the workshop on my GitHub at Brett Hoyer /GenAI.git. Okay. Sorry about that. I'm just seeing that comment now. So we can go over now to getting started with LangGraph. And I promise that the power of this will be evident by the time that we wrap. So here, what we are doing, as I mentioned, LangChain for chains, LangGraph for graphs. Everything in LangGraph is passed through a state graph, and that state is constantly being updated at every node that is visited along the graph. So we have a start point, we have an end point, and we have the ability to append messages to a messages array, a messages list. And this add messages reducer essentially allows us to add messages to the messages array without overwriting the previous messages from previous nodes. So we're just, moving through the graph and appending messages as we go through. This is good and bad, depending on the application that you are working on. You might need to take into account how many messages you are storing because the context window is finite. You can't just supply an LLM with, gigabytes worth of text and expect it to be processing things properly, there's a finite context window, so you might need to only store the last n number of messages to a point, but that is not something that we need to worry about in the immediate. So we're able to build a graph, and you're also able to add other properties to this state. Messages is what we'll be working with, but you can create your own custom properties for more complex workflows. Maybe you'd want one node to know if previously you reached another node. You could add a field for that, for instance. So here, we are going to define a chatbot node. You can think of nodes just how we defined tools in LangChain. There are distinctions, but nodes are essentially just functions that take state and return state from them. The state is constantly being updated. So here, the chatbot, we have a messages array, and what we are doing because of this add messages reducer, the result from this chatbot is being stored in our messages array here. So we can add a node to this graph builder that we have, and graph builder being from the state graph. And we can add edges. So, graphs are comprised of nodes and edges. It is legitimately that simple. What we're doing here is just creating a very simple graph, similar to what we did in LangChain, actually. We're replicating it, where we go from the special start node to the chatbot, and from the chatbot to the special end node, and thus completing our graph. We can compile this graph, and we can display the graph. This is something that is awesome about LangGraph. I've found that this makes it very easy to reason about what you're developing. So here, as I said, we start from the start node, we interact with the chatbot, and then we end. So here we are able to call the stream function on graph in order to supply a user message to the messages, and we can iteratively print out our messages. So what I've written here will ask for user input, and it will execute the graph. It will send the message to the chatbot node, and then it will return. So we can say, so what are we running here? We do not have any tools at our disposal. We just have ChatGPT 3.5 turbo model. So we can say, how old would George Washington be today? So we can see here that we have an AI message being returned from our agent, and we have the content of this message that he stating when he was born, how old he would be today, and various other things, how many tokens were used in the response, etc. So we can add more messages, and how old would his wife be? It depends on when they got married and the age difference between husband and wife. So that's curious. Why didn't we get anything about George Washington? Well, the reason why is because we have no memory of what has happened previously in this graph. Every execution of this graph that we've compiled is independent of one another. So we're saying, we asked a question about George Washington, but a follow-up question has no message history and will be acting independently. So that's how you know that ChatGPT can be seen as an AI agent, because the chat history informs and better informs the agent to provide responses on behalf of your prompts. So this is just a very simple example of how we can use LangGraph in a similar way to LangChain. However, with a little bit more visibility and control over what exactly is happening. It might seem like we've added a bit of complexity, but honestly, it's a little bit freeing knowing a little bit more about what is happening under the hood when building these systems. Now let's add tools to LangGraph. We've shown how we can interact with the LLM, but now I want to add the Tavily search tool that we were using in LangChain. Let's use that very thing now in the LangGraph ecosystem. So we're seeing here, we're importing the very same tool from the LangChain community. And I've specified the max results to be 2 and what is a node in LangGraph. So we're able to get responses from the internet for what is a node in LangGraph. And we can bind that tool to the LLM in order to use it within our chatbot. So much of this code will be the same as what we've seen previously. We are setting our state, telling it to add our messages as a reducer. And we are adding tools and binding them to the LLM, basically making the LLM aware of the tool. So we can run this. And for those of you who are following along or wish to run this offline, I encourage you to add additional sections of code. For instance, you could just type chatbot here and you could run this and it will show you that it is a function and so forth. You can really step through and get a lot more information about each one of these variables that are being set to give you a better understanding of what is comprising this framework and this program that we're building. So we've made the tool available to the LLM. We can also create a tool node. Tool node is something that is built in to LangGraph. And I want to show how LangGraph getting started. So a lot of these examples that we're going through are very closely mirroring the LangGraph getting started. And you can see the tool node. So I've chosen to use the pre-built tool node, but they show you exactly how a tool node can be created and what is the underpinning of it. So it's a node that runs tools, and you can see that it outputs a tool message. So we can just use the pre-built tool node in order to prevent the need to have to actually build this basic tool node ourselves, but it is nice to see how this is built under the hood. So we can use this tool node to add a tool node to our graph. And then we are going to create a conditional edge. So previously, we just executed from start to our chatbot to end. We just immediately returned whatever was returned from our chatbot. But that's not really how a graph is meant to function. We want to be able to reason. Again, our agent is able to reason and invoke functions on our behalf. We want to be able to reason about which paths our agent should take. Our agent might have sub-agents that it's sending messages to, or operating with external data sets if something happens, but not if something else happens. So we are able to create what is called a conditional edge. So if a message from the AI is a tool call, then we know to route our messages to our tools node. Otherwise, if the AI has already gotten the information that it needs, we can route to the end node that is built into LangGraph. You can read all about this in much more detail on LangGraph. Again, I don't want to get bogged down too much in the API details, but we are able to run this. We are creating a graph with a conditional edge from start to chatbot and from tools back to chatbot. And chatbot has a conditional edge to tools. So what exactly does that look like? So before we just went start, chatbot, end. Now the chatbot is made aware of our tools and is actually able to conditionally make requests to this tools node. The tools node will always return its results back to the chatbot. And if we had multiple tools, the chatbot could communicate with multiple tools and only return to the end user when the prompt has been satisfied. So here we can see much the same as before. We can ask a question of our agent here with user input. Now we can ask, how old would George Washington's wife be today? And here we can see that the assistant is actually making requests to this tool agent. And I guess it might be hallucinating a little bit right now. Let's see, what is the weather in Mumbai today? There's sort of some of these are a little bit toy examples. So here we can see, for whatever reason before, and you're able to create additional logic for how many loops these are able to run and stuff. But here we can see that the agent did, in fact, return back to the end user. So it took our prompt, hit the Tavoli tool, returned back to the chatbot, and then went to end, returning us with this from the assistant. So now we can add a tool for querying Postgres. After all, YugabyteDB and Postgres can both store vector embeddings. So I've created a tool that is able to get listings from our database. And it's able to do so by searching text and bedrooms, number of bedrooms. This is, a little bit of a contrived example, but it's pretty cool. We're able to take the text, fetch embeddings using the very same fetch embeddings function that we've been using. And then it can use those embeddings to query our database and provide a response. Here you can see we're fetching embeddings using this function. And we can add this tool to our tools array. So by doing so, now we have the Tavily tool and we have this custom tool that I've written. And let's go ahead and rerun some of the code that ran previously. I've just put all of this in a single block so that it only needs to be executed once. But now we can see, let me print this out. Or actually, we will not print it out. We can show that we have a get listings tool and the Tavily search results tool in our tools array. And we can search, just as we did previously, we can search get listings by the beach with 2 or more bedrooms. So let's see how this will work. Here we can see that we are generating embeddings within our tool. Our assistant has queried our database based on those embeddings, and it is returning listings from our database directly from the graph, which is super cool. We haven't needed to do much that we wouldn't do in our application standard. We've just written a bit of functionality to interface with the database. And we have let the graph know how exactly this tool is to be called in order to achieve these results. So we can change this. I'm not sure that I've tested this, but we can try. We can say, find me houses by the beach. Okay, so it is calling. I was thinking that it might not call the tools node. Let's see. Find the weather by the beach. So here we're invoking the very same graph by calling the stream graph updates method, which is streaming messages. It's printing out as a new event occurs in the graph as we're stepping through the various nodes of the graph with our user input. And it is able to interact with our prompt in multiple different ways. So we could see how we could have tools for searching listings, creating bookings, and so forth, and creating a full system with this framework. So I'm going to move on to adding memory to LangGraph. We're not currently, with our implementation, we're not currently able to ask questions iteratively to arrive at a particular response that we're looking for. Every execution is still independent of one another. So we're going to set up our project very similar to how we did before. We're just building one step at a time. We're binding our tools. We're adding our tools node we're setting a conditional edge. If the last message has a tool call, then visit the tool node. Otherwise, reach the end node. And you can think we might have various other conditional edges in here. We might want to route to a custom function that we wrote, a custom node. We might reach out to a node that has a totally different agent that is calling a totally different model, which would be super powerful if you had a model that was trained to do something very specifically. So what we are adding to the mix from what we've seen previously is this memory saver that is also known as a checkpointer in LangGraph. So here we are able to create a checkpointer at compile time, specifying that we want to store memory in our graph. So we can run this. Looks very familiar. So what this memory allows us to do is to store message history across threads. So think about having an agent that is servicing multiple users. Maybe it's behind an API endpoint. We couldn't store message histories all within one thread, or multiple users using the agent would be having conflicting messages, security concerns, blah, blah, blah. We needn't go into that further. So how you handle this is by adding a config object, config dictionary to our invocation of the graph. And we're able to specify a thread ID. So maybe in a practical sense, a thread ID might link to a conversation ID, maybe a combination of a conversation ID and a user ID might be a good idea. So we are able to invoke this thread, excuse me. And here I'm saying my user input is, hello, my name is Brett, which it is. And then I am getting back a message from the AI saying, hello, Brett, how can I assist you today? And then I'm saying, I'd like to book some travel. And it's saying, sure, I can help with that. Where would you like to travel to? So here we can see that we have a conversation going that is not single transactional. We actually have stuff going on. We can then read the state from our graph per configuration. So passing that same config dictionary, we are able to see a snapshot state of what has been executed at that point in the graph. So we're able to see here that for thread 1, where I executed my prompts, we have my messages written out, and I'm printing them as well. Hello, my name is Brett, all the way to sure, I can help with that. Where would you like to travel to? But when I'm printing out the snapshot 2 with config 2, there are no messages. No messages have actually been fired on thread 2. So were we to try iterating over the messages, this would result in an error. And we can see here, we can print out all of the messages for snapshot 1. Okay, let me see. All right, great. So this is how we can add additional messages. Let me see if on the fly I can make this a little bit more interesting. Let's add again. Let's see, how do I do this? Stream graph updates. I'm going to clear all my outputs. And this is automatically going to use config1. So I don't need to do that myself. I could say, I'd like to go to Hawaii. And I would absolutely love to go back to Hawaii. That sounds like a fantastic choice. Let's see if so it's printing out those messages. Let's see what this looks like. If I create another node, knowing that I've added another message, so to be explicitly clear, we've added another user message saying that I'd like to go to Hawaii to our config1 thread. And we can see that we have the full state snapshot of messages. Those messages are being appended automatically to our thread, preserving this message history and allowing us to have, a continuous conversation. So that is how you can use check pointers and memory in your LangGraph applications. So we might wind up wrapping a bit early. I have one more very cool feature and core building block of LangGraph that I would like to cover. These are merely building blocks. There are many more things that you can look into with LangGraph. For instance, I had mentioned adding custom properties on state. You could use them to pass to your own custom nodes to create your own control flow in a graph. I'm sure there are very complicated examples that you can find online. But what I would like to show next is called human in the loop. Human in the loop being pausing execution of code prior to it running or after it running. So we can ask for human intervention rather than just automatically moving through our graph based on different logic that we've defined. We can actually explicitly wait for a human to verify that what the LLM is deducing, what the agent is choosing to do on our behalf is correct before potentially modifying data or going down a particular path in our graph. So we are instantiating this much the same as before. I've been saying that. But we have added memory. We are building upon our last module. And we are adding one thing here. In addition to adding our check pointer at compile time, we are also adding a tools interrupt. So before a tool is being called, we are asking the execution to stop until a user has explicitly asked us to continue on. So this is a cool thing. We can see this directly within our tools node that we are going to interrupt before executing our tools. So here I am going to run on thread 2. Could have done thread 1, but I guess I just chose to do thread 2 in this example. We're going to invoke our graph in the same way that we did before, but we're going to see how this differs than before. We are going to input, hello, my name is Brett. How can I assist you today? I'd like to book some travel. what's the weather like in DC? So our agent graph knows that it needs to access the internet in order to reason about what the weather is in DC today. It wants to make a tool call to the Tavily search results tool that we've been using. And we can explicitly see that this tool call is being called with the query weather in Washington, DC. So we can use this snapshot that we can get the state of the graph at this present moment in time. And we can print the next property as well as the full snapshot. So we're seeing here that the next property is a tuple with the first value being tools. This is exactly what we'd expect. We haven't returned from our agent. We've paused execution, interrupting before calling our tool. And we are stuck here. Let me see. Do we have a tool call? We can see here that our last message, finish reason from the AI agent, is tool calls, and it is wanting to execute a tool call to the Tavily search results tool. And this is, I presume, an AI message. Sorry for the very long. Yeah, you can see it's of type AI message. So there are user messages and AI messages, human messages and AI messages. So here we can see that the last message on our snapshot is this tool call that we would like to execute. So this, yeah, we don't need to execute this. So in order to opt into moving forward through the graph, of course, we could cancel the operation at this point if we were doing something destructive and didn't want to actually execute this function, this tool. All we have to do is run the graph stream method, passing none, and that same config object that we have been working with. So config is our thread 2 that we use to instantiate this chain, and we can pass none to it, and we will continue printing our values. We can see here that we are calling the tool, and the tool message and the AI message are finally being returned. So we can see that our full snapshot has my initial messages, then an ask for the weather, a call to the tool message is added to the messages array, and then another AI message. So we are constantly keeping tally of what is going on, and we are able to continuously make changes per user input. So now I'm going to add a tool for querying Postgres. So I would like to actually be able to create bookings and fetch listings. So let me see if I can get this working. No promises, absolutely zero promises, but I wanted to run through this. I have created a tool for inserting bookings to the database with the bookings table of the database. So if we go back to Postgres and if we check out the bookings table, we can see that we have start date, end date, customer ID, and so forth. I've seeded a single customer in the database in order to get this working previously. And this tool has been added to the tools array. So I've appended the get listings and create bookings tools to our tools array. So now we have access to the Tavily search results tool, the get listings tool, and the create booking tool. And we are going to rebuild this graph. We're going to do everything that we did previously. We're going to interrupt before tools. Now we just have new tools at our disposal. So I want to get listings by the beach with 2 or more bedrooms. All right. We are getting listings. Of course, this is not a destructive action in a practical sense. I wouldn't want to stop in order to do this, but for sake of demonstration, I have stopped, and we can see that the get listings tool is being called with the text beach and bedrooms 2 as the inputs. And we have continued on in our graph by passing none to the stream method. Get listings has returned several listings for us. So we have ocean, beachfront, and various other listings from our database. So let's see. I'm not sure if this is going to work because I don't know if it is storing all of the IDs. So I would like to see if we print our snapshot. Oh, well, let's be a little smarter. We need to reinstantiate our snapshot based on the fact that we have rerun. And well, this isn't the prettiest thing in the world. We can see that our database has actually stored the ID, the description, and so forth from our tool. So our tool has been stored on the check pointer of our agent in memory. Moving back here, we can see that when fetching listings, I've asked for the ID to be returned because that ID is going to be needed to make a booking. So with the knowledge that we have all of these listings at our disposal. They've been printed out based on our reasoning about and our query. We can ask it to create a booking for the first listing from the 13th to the 15th. Let's see if this will work. So here we can see that it's trying to call the create booking tool, and it's passing the listing ID, which is the ID of the first listing returned from the database, I would assume. It is using customer ID 1, which is the default, and it is setting the dates seemingly improperly. I might need to add additional logic to ensure that the date is of reason, or add to the system prompt to make sure that this is not possible. But this is just a simple demonstration. So let's go ahead and continue execution. We are creating booking, and we can see that the ocean beachfront has successfully been created from 11:13 to 11:05, and it's asking if I need anything else. So I could have created additional tools for deleting bookings, for doing any number of things as a virtual travel agent. I could have also broken down this context into multiple agents operating on multiple nodes so that the context available to a particular agent is small. It might just do something very concrete. It's generally not great to have a very large system prompt that is overly complicated. I found that there's a lot greater chance of hallucination or adverse effects from the agent when doing so. So these are essentially the building blocks of building an agent. I can show our bookings. Let's just show. Let's see, booking ID maybe. The status is pending for whatever reason. I guess that's the default that I set in the schema. And we are seeing here that the ID that was supplied was in fact added for the listing ID and the customer ID. So that is all I have. I hope that you found this interesting. I know that this is all encompassing and probably a little bit exhausting between building agents from a code standpoint, as well as operating with embeddings and vectors in the database world. But at the end of the day, it really is not terribly difficult to get up and running with these various technologies. If I may, since we have just a tiny bit more time before I'm going to sign off here, I will just say that I do have additional resources that you might find interesting if you'd like to build some simple agents or agentic applications. You can see some of the architecture that I've worked with in the past. I've also produced some YouTube videos that you can find on our YouTube channel here at Yugabyte. This blog post in particular, I was able to create embeddings for images using a multimodal model, and was able to find recipes based on ingredients in images. And all of this detail is provided in this blog post. I have also been able to create a distributed movie recommendation engine on YugabyteDB. So while we've been using Postgres for this workshop, just because we could have used Postgres, we could have used YugabyteDB, I like thinking of them as being synonymous in many cases, Postgres being the query layer living on top of YugabyteDB's storage layer, so to speak. I was able to build a distributed system with embeddings being stored across multiple regions. So that is the value proposition of using YugabyteDB for your AI applications. You'll be able to minimize downtime, improve performance potentially. You could pin embeddings that are pertinent only in a particular region to that region for faster lookups, and so on and so forth. As I mentioned, we have a team here at Yugabyte with deep domain experts working on building out all of the vector search and index capabilities found in pgvector and beyond, but on Yugabyte's storage layer. So this is a pretty interesting one that I really put a lot of work into and would highly recommend you check out. This was built on top of Vertex AI's multimodal model for finding movie recommendations and storing them on database nodes across multiple regions. So that is all I have. I hope you found this interesting, and please let me know if you have any questions. You can reach out in Slack. You can reach out to me on X or preferably LinkedIn. And thanks a lot. I hope to hear from you soon, and have a good day.